This lecture is the motion of planets around the sun, 3/13/64. After that, after the bad news you just heard announced, I have some good news for the same reason, that since the exam is coming up on Tuesday, nobody wants to give a lecture that you have to study. So I'm giving you lectures just for the fun of it, for your entertainment. And, all right, I won't be able to give it now. You save all that for the for the end and then make up your mind. The history of our subject of physics had one of the most dramatic moments of the real beginnings was when Newton suddenly understood so much from so little. And the history of this discovery is, of course, the long story about Copernicus, Tycho making his measurements of the positions of the planets, and Kepler finding the laws which empirically describe the motion of these planets. It was then that Newton discovered that he could understand the motion of the planets by stating another law. And you know all this from a lecture on gravitation, so I continue directly from there with a quick summary of that material. In the first place, Kepler observed that the planets went in ellipses around the sun with the sun as the focus of the ellipse. He also observed, he had three observations, he also observed that the air, to describe the velocities, that the area that's swept out by a line drawn from the sun to the orbit is proportional. This area here is proportional to the time. Finally, to connect planets in different orbits, he discovered that the planets with different orbits have periods, or times of rotation around the complete orbit, which bear a 3/2 power ratio to the major axis of the ellipse. If there were circles, to make it easy, it would mean that the time to go around the circle is proportional to the cube, the square of the time is proportional to the cube of the radius of the circle. Now, Newton was able to discover two things from this. First, he noticed that equal areas and equal times meant, from his point of view about inertia, that the material would continue in a straight line at a uniform velocity if it were not disturbed, that the deviations from the uniform velocity are always directed toward the sun, and that equal areas and equal times is equivalent to the statement that the forces are toward the sun. So he used one of Kepler's laws already to deduce that the forces were toward the sun. And then it is easy to argue, especially for the special case of circles, from the third law, that for such circles, the force which would be directed toward the sun would have to go inversely as the square of the distance. The reason for that is something like this. Suppose that we take a certain fractional part of an orbit, some fixed angle of small angle, and a particle has a certain velocity in one part of the orbit and another velocity later on. Then the changes in velocity for a fixed angle are evidently proportional to the velocity. And the changes in velocity during an interval of time, during a fixed time, which is the force, is evidently proportional to the velocity in the orbit times the time that it takes to go across this fraction of the orbit. Divided by the time. So the velocity change is proportional to the velocity, and the time over which that change has taken place is proportional to the time that it takes to go around the whole orbit, because it is a fixed angle, like 1/100th of the orbit. Therefore, the centripetal acceleration, or change per second of the velocity in the direction of the center, is proportional to the velocity on the orbit divided by the time it takes to go around. You can put that in many different ways, because, of course, the time it takes to go around is related to the velocity by this relation set. The speed times the time is the distance around, or rather that the speed times the time is proportional to the radius. And so you can either substitute for the time, obtaining your famous v squared over r, or better, I substitute for the velocity r over t. The velocity is evidently proportional to the radius divided by the time that it takes to go around, so that the centrifugal acceleration goes as the radius and inversely as the square of the time to go around. But Kepler tells us that the time to go around squared is proportional to the cube of the radius. That is, the denominator is proportional to the cube of the radius, and therefore the acceleration toward the center is inversely as the square of the distance. So Newton was able to deduce, in fact Hooke deduced earlier than Newton in the same way, that this force would be inversely as the square of the distance. So from two of Kepler's laws we come only with two conclusions. No one can verify anything that way. This may be of no particular interest because the number of hypotheses entered is equal to the number of guesses that, the number of facts checked is the number of guesses used. On the other hand, what Newton discovered, and which was the most dramatic of his discoveries, was that the third law of Kepler was now a consequence of the other two. Given that the force is toward the sun, and given that the force varies inversely as the square of the distance, to calculate that subtle combination of variations in velocity to determine the shape of the orbit and to discover that it's an ellipse is Newton's contribution. And therefore, he felt that the science was moving forward because he could understand three things in terms of two. As you well know, he understood ultimately many more than three things, that the orbits, in fact, are not ellipses, that they perturb each other, that the motion of the Jupiter satellites is also understood, the motion of the moon around the Earth, and so on. But let us just concentrate on this one item, in which we disregard the interactions of one planet with another. Newton, therefore, I can summarize what Newton said, then, in this way about a planet, that the changes in the velocity in equal times are directed toward the sun, and in size they are inversely as the square of the distance. It is now our problem to demonstrate, and it is the purpose of this lecture mainly, to demonstrate that, therefore, the orbit is an ellipse. It is not difficult when one knows the calculus and to write the differential equations and to solve them to show that it's an ellipse. We, I believe in the lectures here, or at least in the book, calculated the orbit by numerical methods and saw that it looked like an ellipse. That's not exactly the same thing as proving that it's exactly an ellipse. The mathematics department ordinarily is left the job of proving it's an ellipse so that they have something to do over there with their differential equations. I prefer to give you a demonstration of its ellipse in a completely strange and unique, a different way than you're used to. I am going to give what I will call an elementary demonstration. By elementary does not mean easy to understand. Elementary means that nothing, very little, is required to know ahead of time in order to understand it, except to have an infinite amount of intelligence. It is not necessary to have knowledge, but to have intelligence in order to understand an elementary demonstration. There may be a large number of steps that are very hard to follow, but each step does not require already knowing calculus, already knowing Fourier transforms, and so on. So by an elementary demonstration, I mean one that goes as far back as one can with regard to how much has to be learned. Of course, an elementary demonstration in this sense could be first to teach calculus and then to make the demonstration. This, however, is longer than the demonstration which I wish to present. Secondly, this demonstration is interesting for another reason, is that it uses completely geometrical methods. We have, perhaps some of you are delighted in geometry in school, with the fun of having your ingenuity to discover the right construction lines. The elegance and beauty of geometrical demonstrations is often appreciated by lots of people. On the other hand, after Descartes, all geometry can be reduced to algebra. And today, all mechanics and all these things are reduced to analysis with symbols on pieces of paper, and not by geometrical methods. On the other hand, at the beginning of our science, that is in the time of Newton, the geometrical method of analysis in the historical tradition of Euclid was very much the way to do things. And as a matter of fact, Newton's Principia is written in a practically completely geometrical way. All the calculus things being done by making geometric diagrams. We do it now by writing analytic symbols on the blackboard, but for your entertainment and interest, I want you to ride in a buggy for its elegance instead of in a fancy automobile. So we're going to derive this fact by purely geometrical arguments, well, by essentially geometrical arguments, and because I don't know what that means. Anything precise, I don't know what it means, like purely geometrical. But essentially geometrical arguments, and see how well we get on. So our problem is to demonstrate that if this is true, that the changes in velocities are directed toward the sun, and that the inversely as the square of the distance in equal times, that the orbit is an ellipse, we then have first to understand we must start with something. We first must know what an ellipse is. If there is no available definition of an ellipse, it is going to be impossible to demonstrate the theorem. And furthermore, if you cannot understand the meaning of this proposition, of course, you also cannot demonstrate the theorem. So many people have said, oh, yeah, but you've got to know something about an ellipse. I know. But that's part of it. You can't state the statement otherwise. And also you have to have some understanding of this idea. That's also true. But beyond that, I think we don't need much extra knowledge, but a large amount of attention, please, and careful thinking. That's not easy, and it's quite a job, and it's not worthwhile. It's much easier to do it by the calculus, but you're going to do it that way anyway, and you must remember that this is just to see how it would look if you did it a different way. There are several ways of defining an ellipse, and I have to choose one, and I will suppose that the one with which everyone is familiar is the fact that an ellipse can be made, or an ellipse is the curve that can be made by taking two strings at two tacks, and one string rather, from two tacks and putting a pencil in here and going around, or mathematically, it's the locus, nowadays they say the set of all points, all right, the set of all points, such that the sum of the distance fp and the distance f prime p to two fixed points remains constant. I suppose you know that that's the definition of an ellipse. You may have heard another definition of an ellipse if you wish. These 2 points are called the foci, and this focus means that light emitted from F will bounce to F prime from any point on the ellipse. Let me just demonstrate the equivalence of those two propositions at least. So the next step is to demonstrate that light will be reflected from F to F prime. The light is reflected as though the surface here were a plane tangent to the actual curve. What I therefore have to demonstrate is this. And you know, of course, that the laws of reflection for light from a plane is that the angle of incidence and reflection are the same. Therefore, what I have to prove is this, that if I were to draw a line here, such that its angles made with the two lines FP and F prime P are equal, that line is then tangent to the ellipse. Proof. Here's the line drawn as described. Make the image point of F prime in this line. That is to say, extend the perpendicular from F prime to the line, the same distance on the other side, to obtain G prime, the image of F prime. And now connect the point P to G prime. Notice, because of the equal angles, that this angle here is the vertical angle. Well, this angle is equal to this angle because these two right triangles are exactly the same. It's an image, so this side is the same as that side, and these two angles are equal. This is a straight line. So that the PG part here is exactly equal to the F prime P part, and this, incidentally, FG prime is a straight line, so that the FP plus F prime P, which is the sum of these two distances, is in fact FP plus G prime P, because F prime P equals G prime P. And that's together FG prime. Now the point is, if you take any other point on the tangent, say Q, and you took the sum of these two distances to Q, it's easy to see that the distance F prime Q is again the same as G prime Q. So that the sum of these two distances, F prime Q to F, is the same as the distance from F to Q and Q to G prime. In other words, the sum of the distances from the two foci on any point on the line is equal to the distance from F to G prime by going up to that point and across. Evidently larger, evidently always larger than going on the straight line across. In other words, the sum of the two distances to a point Q is greater than it is for the ellipse. For any point Q except for point P. For any point on this line, then, the sum of the distances to these 2 points is greater than it is for a point on the ellipse. Now, I take the following to be evident, and perhaps you can devise a proof to satisfy you, that if the ellipse is the curve in which the sum of the 2 points is a constant, that the points outside the ellipse have the sum to the 2 points greater, and the points inside the ellipse have the sum to the 2 points less. So that since these points on the line have a sum greater than a point on the ellipse, all this line lies outside the ellipse with the sole exception of the point P, whence it must be tangent and must not intersect in 2 points, nor ever come inside. All right, so the thing is therefore tangent, and we know that the reflection law is right. I have another property to describe about an ellipse, the reason for which will be completely obscure to you, but it's something which I'll need later in this demonstration. May I say that although the methods of Newton were geometrical, he was writing in a time in which the knowledge of the conic sections was the thing that everybody knew very well. And so he perpetually uses very, for me, completely obscure properties of the conic sections. And I have, of course, to demonstrate my properties as I go along. I would like, however, for you to take the same diagram again, which I made here, and draw it over again. It's drawn exactly the same. Here's F prime and F. There's that tangent line. Here's the image point G prime of F. However, I would like you to imagine what happens to the image point G prime as the line point P goes around the ellipse. It is evident, as I already indicated, that PG prime is the same as F prime P, so that FP plus F prime P is a constant means that FP plus PG prime is a constant. In other words, that FG prime is a constant. In short, the image point G prime runs around the point F in a circle of constant radius. All right? At the same time, I draw a line from F prime to G prime, and I find my tangent is perpendicular to it. That's the same statement as all that was before. And I just want to summarize that to remind you of a property of an ellipse, which is this: that as a point G prime goes around a circle, a line drawn from an eccentric point to this point G prime, this is an off-center point to the point G prime, will always be perpendicular to the tangent of the ellipse, or the other way around. The tangent is always perpendicular to the line or line drawn from an eccentric point. All right? That's all. We'll come back to it and we'll review it again, so don't worry. That's just a summary of those, some of the properties of an ellipse starting from the facts. That's the ellipse. Now, on the other hand, we have to learn dynamics. We have to put them together. So now we have to explain what dynamics is all about and what this proposition, that's the geometry now for the mechanics, what this proposition means. What Newton means by this is this: that if this is the sun, for instance, the center of the attraction, and at a given instant a particle were to say be here, and let me suppose that it moves to another point from A to B in a certain interval of time, then were there no forces acting toward the sun, this particle would continue in the same direction and go exactly the same distance to a point C. But during this motion, there's an impulse toward the sun, which, for the purposes of analysis, we will imagine all occurs at the middle instant. In other words, at this instant. In other words, we concentrate all our impulses in an approximate way of thinking to this middle moment. And therefore the impulse is in the direction of this sun, and this might represent the change in motion. That means that instead of this moving to here, it moves to a new point, which is capital C, which is different than C because the ultimate motion is this motion compounded from the original plus the additional impulse given from the center toward the center of the sun. So that the ultimate motion is along the line BC, and at the end of the second interval moment of time, the particle will be at C. I emphasize that CC, this is small c, the large C, small c, is parallel to and equal to BV, let us say, the impulse given from the sun. It is therefore parallel to a line from B to the center of the sun. Finally, the rest of the statement is that the size of BV will vary inversely as the square of the distance as we go around the orbit. I have drawn this same thing over again here exactly the same way, no change at all, except in color. Makes it more interesting. Here's the motion that the particle would has in the first instant of time, and the motion which would have continued to have if it were to continue for the second interval of time with no force. May I point out to you that the areas that would be swept through in that case would be equal during those two intervals of time. For these two distances, AB and BC, are evidently equal. And therefore the two triangles SAB and SB little c, which are the two areas, will be equal, for they have equal bases and a common altitude. as if you extend the base and draw the altitudes. It's the same altitude for both triangles, and since the bases are equal, the areas then swept through are equal. On the other hand, the actual motion is not to the point little c, but to the point capital C, which differs from the position little c by a displacement in the direction of the sun at the moment b. That is, in the blue line, parallel to the original blue line. Now, I would like to point out to you that the area that would be occupied, which would be swept out in that second interval of time, even if there were a force, namely the area SB capital C, is the same as the area that there would be if there were no force, namely SB little c. The reason is that we have two triangles which have a common base and who have an equal altitude, for they lie between parallel lines. Since the area of the triangle SB capital C and the triangle SAB are equal, but since those points A, B, and C represented positions in succession at equal times in the orbit, we see that the area moved through in equal times are equal. We can also see that the orbit remains a plane, that the point C being in the plane and the line CC being in the plane of ABS, the remaining motion is in the plane ABS, and I have drawn a succession of such impulses around this imaginary polygonal orbit. Of course, the actual orbit, to find the actual orbit, we need to make the same analysis with a much smaller interval of time, with a much finer rate of impulsing, until we get the limiting case in which we have a curve. And in the limiting case in which we have a curve, the area swept by this thing, where the curve will lie in a plane and the area swept will be proportional to the time. So that's how we know that we have equal areas in equal times. The demonstration you have just seen is an exact copy of one in the Principia Mathematica by Newton. And the ingenuity and delight which you may or may not have gotten from it is that already existing in the beginning of time. Now, the remaining demonstration is not one which comes from Newton, because I found I couldn't follow it myself very well because it involved so many properties of conic sections. So I cooked up another one. We have equal areas in equal time. I would like now to consider what the orbit would look like if, instead of using equal times, one were to think of the succession of positions which correspond to equal angles from the center of the sun. In other words, I repicture the orbit with the diagram, with the succession of points J, K, L, M, N, which correspond not to equal instants, as they did in the diagram before, but rather equal angles of inclination from the original position. To make this a little bit simpler, although it's not at all essential, I have supposed that the original motion was perpendicular to the sun at the first point, but that's not essential. It just makes the diagram cleaner. Now we know from the proposition previously that equal angles occupy equal times to be swept through them. Now listen, I would point out to you that equal angles mean that the areas, equal angles, which is what I'm aiming for, means that areas are not equal. No, but they are proportional to the square of the distance from the sun. For if I have a triangle of a given angle, it is clear if I make two of them that they are similar, and the proportional area of similar triangles is proportional to the square of their dimensions. Equal angles therefore means, since areas are proportional to time, equal angles therefore means that the times of this to be swept through these equal angles are proportional to the square of the distance. In other words, these points J, K, L, and so on do not represent pictures of the orbit at equal times, no, but they represent pictures of the orbit with successions of times which are proportional to the square of the distance. Now, the dynamical law is that there are equal changes in velocity. No, that the changes in velocity vary inversely as the square of the distance from the sun. That is, the changes of velocity in equal time. Another way of saying the same thing is that equal changes of velocity will occupy times proportional to the square of the distance. It's the same thing. If I take more time, I get more change in the velocity. And in order to, although they are falling off for equal times inversely as a square, if I make my times proportional to the square of the distance, then the change in velocity will be equal. Or, the dynamical law is equal changes in velocity occur in times proportional to the square of the distance. But look, equal angles were times proportional to the square of the distance. And so we have the conclusion from the law of gravitation that equal changes of velocity will occur in equal angles in the orbit. That's the central core from which all will be deduced. That equal changes in velocity occur when the orbit is moving through equal angles. So I now draw on this diagram a little line to represent the velocities. Unlike the other diagram, those lines are not the complete line from J to K. For in that diagram, those were proportional to the velocities, for the times were equal, and the lengths divided by equal times represented the velocities. But here I must use some other scale to represent how far the particle would have gone in a given unit of time, rather than in the times which are in fact proportional to the square of the distance. So these represent the velocities in succession. It is quite difficult in that diagram to find out what the changes are. I therefore make another diagram over here, which I'll call a diagram of the velocities, in which I draw a picture on a magnified scale only for convenience. These are supposed to represent exactly these same lines. This would represent the motion per second of a particle at J, or in a given interval of time at J. This would have represent the motion that a particle would have made from a given origin, from the beginning in a given interval of time. And I put them all at a common origin so that I can compare the velocities. So I have then a series of the velocities for the succession of these points. Now, what are the changes in the velocity? The point is that in the first motion, this is the velocity. However, there's an impulse toward the sun. And so there is a change in velocity indicated by the green line that produces the second velocity, vk. Likewise, there's another impulse toward the sun again, but this time the sun is at a different angle, which produces the next change in the velocity, VL, and so on. Now, the proposition that the changes in the velocities were equal for equal angles, which is the one that we deduced, means that the length of these succession of segments are all the same. That's what it means. And what about their mutual angles? Since this is in the direction of the sun at this radius, since this is in the direction of the sun at that radius, and since this is in the direction of the sun at that radius, and so on, and since these radii each successively have a common angle to one another, so it is likewise true that these little changes in the velocity have mutually to one another equal angles. In short, we are constructing a regular polygon. A succession of equal steps, each turned to a equal angle, will produce a series of points on the surface, on the line, a circle. It will produce a circle. Therefore, the end of the velocity vector, if we call it that, the end of these velocity points, I suppose you know what a vector is, in this elementary description, will lie on a circle. I drew the circle again. I review what we found out. I take the continuous limit, where the intervals of angle are very tiny indeed, to obtain a continuous curve. Let theta be the angle, total angle, to some point P, and let Vp represent the velocity of that point in the same way as before. Then the the diagram of velocities will look like this. This is the origin of the velocity diagram, the same always as over there, and this is the velocity vector corresponding to this point P. Then this lies on a circle, but always not necessarily the center of that circle. However, the angle that you've turned through in the circle is the same theta as here. The reason for that is that the angle turned through from the beginning by this thing is proportional to the angle turned through by the orbit, because it's a succession of the same number of small angles. And therefore, it will produce a circle. Therefore, the end of the velocity vector, if we call it that, the end of these velocity points, I suppose you know what a vector is, in this elementary description, will lie on a circle. I drew the circle again. I review what we found out. I take the continuous limit, where the intervals of angle are very tiny indeed, to obtain a continuous curve. Let theta be the angle, total angle, to some point P, and let Vp represent the velocity of that point in the same way as before. Then this the diagram of velocities will look like this. This is the origin of the velocity diagram, the same always is over there. And this is the velocity vector corresponding to this point P. Then this lies on a circle, but always not necessarily the center of that circle. However, the angle that you've turned through in the circle is the same theta as here. The reason for that is that the angle turned through from the beginning by this thing is proportional to the angle turned through by the orbit, because it's a succession of the same number of small angles. And therefore, this angle in here is the same angle as in here. So here's the problem. Here's what we've discovered, that if we draw a circle and take an off-center point, then take an angle in the orbit, any angle you want in the orbit, and draw the corresponding angle inside this constructed circle, and draw a line from the eccentric point, then this line will be the direction of the tangent. Because the velocity is evidently the direction of motion at the moment, and is in the direction of the tangent to the curve. So our problem is to find a curve such that if we draw a point from an eccentric center, the direction of the tangent to that curve will always be parallel to that when the angle of the curve is given by the angle in the center of that circle. In order to make still clearer why it's going to come out of this thing, I'll turn the velocity diagram of 90 degrees about so that the angles correspond exactly and are parallel to each other. This diagram under here, then, is precisely the same diagram as the one you see above, but turned 90 degrees only to make it easier to think. This, then, is the velocity vector, except that it's turned 90 degrees. Because the whole diagram is turned 90 degrees. That is, this is perpendicular evidently to that. And therefore, this is evidently perpendicular to that. In short, we must find a curve such that if we put the orbit in it, I think I've started. Yes, well, I'll just say it and then I'll draw it again. If we put the orbit in it, at a given point here where this line intersects the orbit, never mind the scales, they're all imaginary, I mean, it's all in proportion. Where this line intersects the orbit, the tangent should be perpendicular to that line from an eccentric point. I draw again to show you how it is. You know now what the answer is, but here's a picture again of the same velocity circle. But this time the orbit is drawn inside at a different scale, so that we can see this picture laid right over this picture, so the angles correspond. So since the angles correspond, I can draw the single line to represent both the point P on the orbit and the point little p on the velocity circle. Now what we have discovered is that the orbit is of such a character that a line drawn from the eccentric point here, from an extension of this point onto a circle outside, will always be perpendicular to the tangent to the curve. Now that curve is an ellipse, and you can find that out by the following construction. Construct the following curve, because the curve I'm going to construct will satisfy all the conditions. Construct the following curve. Always take the perpendicular bisector of this line and ask for its intersection with the other line, CP, and call that intersection point capital P. This is the perpendicular bisector. Now I'll prove two things. First, that the locus of this point that's been generated there is an ellipse. And second, that this line is a tangent there too, that is, to the ellipse, and therefore satisfies the conditions and all is well. First, that it's an ellipse. Since this was the perpendicular bisector, it is at equal distances from O and from little p. It is therefore clear that capital P little p is equal to PO. That means that CP plus PO, which is therefore equal to OP plus capital P little p, is the radius of the circle, which is evidently constant. So the curve is an ellipse, for the sum of the two distances is a constant. And next, its tangent, this line is tangent to the ellipse, because since this triangle, these two triangles, the perpendicular bisector, the two triangles are congruent, this angle here is equal to this angle here. But if I extend this line on the other side, so also is that angle equal. So therefore the line in question makes an equal angle with the two lines to the foci, but we proved that that was one of the properties of an ellipse, the reflection property. Therefore, the solution to the problem is an ellipse, or the other way around really is what I proved, that the ellipse is a possible solution to the problem, and it is the solution. So the orbits are ellipses. Elementary but difficult. I have considerable more time, and so I'll say a few things about this. In the first place, I would like to say how I got this demonstration. The fact that the velocities went in a circle, the demonstration up to this point, was due to Mr. Farno, and I read it. And after that, to prove that it was an ellipse took me an awful long time. That is the obvious, simple step. You turn it this way and you draw that and all that. Very hard. And like all these elementary demonstrations, they require a large amount, like any geometrical demonstration, requires a large amount of ingenuity. But once presented, it's elegantly simple. I mean, it's just finished. But the fun of it is that you've made a kind of carefully put together piece of pieces. It is not easy to use the geometrical method to discover things. It is very difficult, but the elegance of the demonstrations after the discoveries are made is really very great. The power of the analytic method is that it's much easier to discover things and to prove things, but not in any degree of elegance. Just a lot of dirty paper with X's and Y's and crossed out cancellations and so on. I would like to point out a number of interesting cases. It, of course, can happen that the point O lies on the circle, or even that the point O lies outside the circle. It turns out that the point O lying on the circle does not produce, of course, an ellipse. It produces a parabola. And the point O lying outside the circle, which is another possibility, produces a different curve, a hyperbola. I leave some of those things for you to play with. On the other hand, I would like now to make some application of this and to continue the argument that Mr. Farno originally made for another purpose. He was going in a different direction. I'd like to show you that. What he was trying to do was to make an elementary demonstration of a law which was very important in the history of physics in 1914. And that has to do with the so-called Rutherford's law of scattering. If we have an infinitely heavy nucleus, which we don't have, but we suppose, and if we shoot a particle by that nucleus, then it will be repelled by an inverse square law because of the electrical force. If Q sub E is the charge on an electron, the force, then the charge on the nucleus is Z times Q sub electron, where Z is the atomic number, then the force between the two things is given by 4 pi epsilon naught times the square of the distance, which for simplicity I will write temporarily as Z over R squared, a constant over R squared. That's, excuse me, never mind this. I don't know whether you've done this in the class or not, but I'll suppose that I'll define another thing, because Q electron squared over 4 pi epsilon naught will be written E squared for short. Then this thing can just Z E square over R square. Anyway, that's the force inversely is the square of the distance, but it's a repulsion. And now the problem is the following. If I shoot a lot of particles at these nuclei where I can't see the nuclei, how many of them will be deflected through various angles? What percentage will be deflected more than 30 degrees? What percentage will be deflected more than 45 degrees? And how are they distributed in angle? And that was the problem that Rutherford wanted solved. And when we had the correct solution, he then checked it against experiment. And he found that the ones that were supposed to be deflected through large angles were not there. In other words, the number of particles deflected through large angles was much less than you would think. And he therefore deduced that the force was not as strong as 1 over R squared for small distances, because it is obvious that to get the large angle, you need a lot of force, and it corresponds to the ones that hit almost head-on. So those which come very close to the nucleus do not seem to come out the way they ought to. And the reason is that the nucleus has a size, and that I got the story backwards. If the nucleus had a big size, then those which were supposed to come out at large angles wouldn't get their full force, because they would get inside the charge distribution and would be deflected less. I got the story backwards, excuse me, I got mixed up. I start again. Rutherford deduced how it should go if all the forces were concentrated at the center. In his day, it was supposed that the charge in an atom was distributed uniformly over the atom. And in order to discover this distribution, he thought that if he scattered these particles, they would show a weaker deflection. They would never show a very large deflection corresponding to a very close approach to the repulsion center, because the close approach has no center. He, however, did find the large angle deflections and deduced that the nucleus was small and that the atom had all its mass at a very small central point. I got it backwards. It was later that it was demonstrated by the same thing again, that the nucleus has a size, but the first demonstration was that the atom is not as big for this kind of electrical purposes as the whole atom is known to be. That is, all the charge was concentrated at the center, and thus the nucleus was discovered. However, we need now, to understand this, we need to know what the law is for the angle of deflection here, and that we can obtain in this way. Suppose that we do the same thing as we did before, and we draw the orbit. Here's the charge, and here is the motion of a particle going around, only this time it's repulsion. I start the picture at this point for the fun of it, and I draw my velocity circles as before. This is the velocity. We know that the velocity, the initial velocity at this point, we know that the velocities, I should use the same colors so you know what I'm doing, that the velocity, this should be then blue, the velocity, this orbit is red. Now, the velocity changes lie on a circle, but the changes in the velocity this time are repulsions, and the sign is reversed, and after some minor thought, you can see that the deflections go like that, and that the center of the calculation lies, the center of this thing, which is used to be called the origin of the velocity space, O, lies on the outside of the circle. And the succession of small velocity changes are lying on the circle, and the succession of velocities then in the orbit are these lines, until a very interesting point comes, until we get to this tangent. At this tangent point to the curve, what does it mean? It means that all the changes in velocity are in the direction of the velocity, but the changes in the velocity are in the direction of the sun. And that means that this velocity in this part of the diagram is in the direction of the sun, because it's in the direction of the changes. That is to say, this point here, as we approach this point here, which I could call X, say, it corresponds to coming from infinity toward the sun along a line here. That is, very far out, we are directed toward the sun very accurate, closely, or not the sun, but the nucleus. And then as it comes around here, this diagram should be the other way. The arrows should be, I got the changes the wrong way in time. Comes around here and goes out this way. And going out that way corresponds to going with a velocity off in this direction. Now, if we draw then the orbit more carefully, it will look very much like this. It goes around like this. If I call this point here velocity infinity, then the velocity that the particle has at the beginning is velocity infinity. If on the same scale I call the radius of this circle v sub the velocity corresponding to the radius of the circle, well, then we have all the equations. We're going to make up some equations. I'm not going to do it completely geometrically, but to save time and so on, I've done all the work. One should not ride in the buggy all the time. One has the fun of it and then gets out. Now, first I want to find the velocity of the center, the velocity of the radius of the velocity circle. In other words, I'm now going to come down and make some of these geometric things more analytic. I'll suppose that the force is some constant, the acceleration rather, is some constant over r squared. For gravity, this constant is gm. And for electricity, it's ze squared over m. Over m because of the acceleration. That is to say the changes in velocity are always equal to z over r squared times the time. Now let us suppose that we call alpha a constant, which is a constant for the motion, the area swept by the orbit per second. That is then this way, that the time, if I wanted to change this to angle, I have the following. R squared d theta would be the area. If I divide that by the rate that area is swept through, this tells me how much time it takes to sweep an angle. The time is then, for given angles, is proportional to the square of the distance. All this I'm saying now analytically, what I said in words before. Substitute this delta t in here to find out how the changes in the velocity are with respect to angle, and one obtains r squared delta theta over alpha. Or the r squares cancel, and it means that the changes in velocity are, as advertised, for equal angles, equal. Now then, in the velocity diagram, although this isn't the piece of the orbit that you can get to, never mind. These are changes in the velocity, and these are changes in the angle, in the orbit. So delta v is also equal, by the geometry of that circle, to the radius of the circle, which I call Vr, times delta theta. In other words, we have that the radius of the velocity circle is equal to z over alpha, where alpha is the rate of area swept per second, and z is a constant having to do with the law of force. Now, the angle through which this planet has deflected is this one here, and I call it phi, is the angle of deflection from the planet, I mean the charged particle from the nucleus. It is evident from my discussion that that's the same as this angle in here, phi, because these velocities are parallel to the two original directions. It is clear, therefore, that we have we can find phi if we can get the relation with v infinity and vr. You see, look, tangent of phi over 2 is equal to vr over v infinity. And that gives us the angle. The only thing is that we have to substitute for vr z over alpha r. Alpha. And now we have that much. Now, it doesn't do us much good until we know alpha for this orbit. An interesting idea is this, is to think of this thing as approaching this so that if there were no force, it would miss by a certain distance, b. This is called the impact parameter. We imagine a thing comes from infinity, aimed for the nucleus, for the force center, but it's missing. Because it misses, it's deflected. By how much is it deflected if it was aimed to miss by b? That's the question. If it's aimed to miss by a distance b, how much will it get deflected? So I need now only determine how alpha is related to b. V infinity is the distance gone in 1 second. So if I were to draw way out here a horrible looking area, a triangle, of a terrible looking triangle, then I've got a factor 2 somewhere. Yeah, the area of a triangle is 1/2 r squared. There are 2 factors 2, which you will straighten out, please, when the time comes. There's a half in here, and there's a half somewhere else. Now, which I'm now going to make. The area of this triangle is the base, v infinity, times the height, b, times a half. So now that area, that triangle is a triangle through which a particle would sweep, with the radius would sweep in 1 second, and this is therefore alpha. So therefore we have that this goes as z over b v infinity squared. That tells us then, given the impact distance, the aiming accuracy, what angle we would find in the deflection in terms of the speed at which the particle approaches and the known law of force. So it's completely finished. One more thing, though, that's rather interesting is suppose you would like to know with what probability, what chance is there of getting a deflection more than a certain amount. Let's say you pick a certain phi phi 0, say, and you want to make sure that you get greater than phi 0. That only means that you have to hit inside an area closer than the B which belongs to that phi. Any collision closer than B will produce a deflection bigger than phi naught, where B is B naught, say, belonging to phi naught through this equation. If you come further away, you'll have less deflection, there's less force. So therefore, the so-called cross-section area that you have to hit for a deflection to be greater than phi, I will leave off the naught, is pi b squared, where b is z over v infinity squared tangent squared phi over 2. Phi, tangent phi over 2 by this thing. In other words, it is or pi z square v infinity square tangent square phi over 2. And that's the law of Rutherford scattering that tells you the probability, the area that you have to hit, the effective area that you have to hit in order to get a deflection more than a certain amount. This z is equal to ze square over m. This is the fourth power. And it's a very famous formula. It's so famous that, as usual, it wasn't written in this form when it was first deduced. And so I, just for the famousness of it, will write it in a form, well, I'll leave you to write it in a form that's, I'll write just the answer, and I'll let you see if you can show it. Instead of asking for the cross-section for a deflection greater than a certain angle, we can ask for the piece of cross-section, which sometimes read d sigma, that corresponds to deflection in the range d phi, that the angle should be between here and there, within the range d phi. You just have to differentiate this thing, and the final result for that thing is given as a famous formula of Rutherford, which is for z squared d fourth times 2 pi sine phi d phi divided by 4 n squared v infinity to the fourth power times the sine of the fourth power of phi over 2. This I write only because it's a famous one. It comes up very much in physics. The combination 2 pi sine phi. We have that the radius of the velocity circle is equal to z over alpha, where alpha is the rate of area swept per second, and z is a constant having to do with the law of force. Now, the angle through which this planet has deflected is this one here, and I call it phi. Is the angle of deflection from the planet, I mean the charged particle from the nucleus. It is evident from my discussion that that's the same as this angle in here, phi, because these velocities are parallel to the two original directions. It is clear, therefore, that we can find phi if we can get the relation with v infinity and vr. You see, look, tangent of phi over 2 is equal to vr over v infinity. And that gives us the angle. The only thing is that we have to substitute for vr z over alpha r, alpha. And then we have that much. Now, it doesn't do us much good until we know alpha for this orbit. An interesting idea is this, is to think of this thing as approaching this so that if there were no force, it would miss by a certain distance, b. This is called the impact parameter. We imagine a thing comes from infinity, aimed for the nuclear, for the force center, but it's missing. Because it misses, it's deflected. By how much is it deflected if it was aimed to miss by b? That's the question. If it's aimed to miss by a distance b, how much will it get deflected? So I need now only determine how alpha is related to b. V infinity is the distance gone in 1 second. So if I were to draw way out here a horrible looking area, a triangle, a terrible looking triangle, then got a factor 2 somewhere. Yeah, the area of a triangle is 1/2 r squared. There are 2 factors 2, which you will straighten out, please, when the time comes. There's a half in here, and there's a half somewhere else. Now, which I'm now going to make. The area of this triangle is the base, v infinity, times the height, b, times a half. So now that area, that triangle is a triangle through which a particle would sweep, with the radius would sweep in 1 second, and this is therefore alpha. So therefore we have that this goes as z over b v infinity squared. That tells us then, given the impact distance, the aiming accuracy, what angle we would find in the deflection in terms of the speed at which the particle approaches and the known law of force. So it's completely finished. One more thing, though, that's rather interesting is suppose you would like to know with what probability, what chance is there of getting a deflection more than a certain amount. Let's say you pick a certain phi 0, say, and you want to make sure that you get greater than phi 0. That only means that you have to hit inside an area closer than the b which belongs to that phi. Any collision closer than b will produce a deflection bigger than phi naught, where b is b naught, say, belonging to phi naught through this equation. If you come further away, you'll have less deflection, there's less force. So therefore, the so-called cross-section area that you have to hit for a deflection to be greater than phi, I will leave off the naught, is pi b squared, where b is z over v infinity squared tangent squared phi over 2. Phi, tangent phi over 2 by this thing. In other words, it is or pi z square v infinity square tangent square phi over 2. And that's the law of Rutherford scattering that tells you the probability, the area that you have to hit, the effective area that you have to hit in order to get a deflection more than a certain amount. This z is equal to ze square over m. This is the 4th power. And it's a very famous formula. It's so famous that, as usual, it wasn't written in this form when it was first deduced. And so I, just for the famousness of it, will write it in a form, well, I'll leave you to write it in a form. I'll write just the answer, and I'll let you see if you can show it. Instead of asking for the cross-section for a deflection greater than a certain angle, we can ask for the piece of cross-section, which sometimes read d sigma, that corresponds to deflection in the range d phi, that the angle should be between here and there, within the range d phi. You just have to differentiate this thing, and the final result for that thing is given as a famous formula of Rutherford, which is for z squared d fourth times 2 pi sine phi d phi divided by 4 n squared v infinity to the 4th power times the sine of the 4th power of phi over 2. This I write only because it's a famous one. It comes up very much in physics. The combination 2 pi sine phi d phi is really the solid angle that you have in range d phi. So in a unit of solid angle, the cross-section goes inversely as the 4th power of the sine of phi over 2, and it was this law, which was discovered to be true for scattering of alpha particles from atoms, which showed that the atoms had a hard center in the middle and have a nucleus, and it was by this formula that a nucleus was discovered. Thank you very much. Yeah. Right. This one? Oh, I should have pulled that down again.
How did you define an angle? You just define it as...
The other way around. I said, if a line at P makes equal angles to these two things, then it is tangent. Now, I proved that if it made equal angles with these two things, that it lies outside the ellipse, except at one point, and it therefore is tangent. See, if a line can lie inside the curve, it's not tangent, right? If it never goes inside the curve and does touch the curve, then it must be tangent. Well, I proved that if the line made equal angle, I went backwards. Instead of saying given the tangent, I said if a line makes equal angles, I'd prove it's tangent. And then I suppose there's only one tangent and this and that, you know. Right, it's backwards. But these things, these demonstrations have always to be made very carefully. If you try to do it the other way, it's quite difficult to start with a tangent, because you have to have a definition of a tangent. I can do it the other way. I had originally another way. You want to see a demonstration the other way? It's rather amusing, so I'll show it to you. Suppose that you say this, that by a tangent you mean this, that if you were to take two successive points on the ellipse. Now wait, I know, but it's a definition. If you take 2 points on the ellipse and let this one approach that one, then this line becomes a tangent, right? I mean, it goes through these 2 points. Now, the idea is, the reason the angles have to be equal is something like this. I'll draw a magnified view of these 2 things coming into the tangent, to the ellipse here, which is practically a straight line. In fact, for the magnified view, it's the tangent that we're looking for. Now, suppose then I move to another point, essentially on the tangent, and I should again be on the ellipse. I mean, it's the same point. It's still on the ellipse for small distances, right? Or effectively on the ellipse for small distances. But you see, this line is shorter, and this line is longer. This line is shorter because this is an incline here. You see, so when you move this point from here to here, the distance to here gets less by, if I would write down a graph of perpendicular, by this little distance. It could be longer, depending on the tilt. But if I draw it the way I've drawn it, then it's shorter from that now, all right? In the same manner, this line here is longer by dropping the same corresponding perpendicular the other way, right? But if this is to be on the ellipse, the lengthening of one string and the shortening of the other string have to be equal. Because it stays on the ellipse, so if I straighten one string longer, the other longer, so that this thing must equal this thing, but there are 2 little triangles on the same base. So the angles must be equal. And these 2 angles are equal. Another way to look at it very crudely is, to get the general idea is that the take-up of this string as you move along here depends on this angle. And the outgo of this string as you move along here depends on that angle. And because they have to be equal to stay on the ellipse, those angles are equal. That's the idea, only you make it refined. That's the other way around. But I felt that this one was more classy because it was more mysterious. And also it got me to this picture. Did I forget to pull this down when I was talking about this? Oh, that's too bad. Oh, that's too bad, because I made it for the sole purpose of showing us the same thing. I'm sorry. It's exactly the same. Yeah.
In this diagram here, shouldn't this velocity,
yeah.
Shouldn't this velocity be the...
No, it's a repulsion. It's a repulsion, electrostatic repulsion. So in the case of repulsion, it's slowed down as it comes in. I got mixed up with the signs. These should be this way, see, as time goes on. And it's slowed down, so this is less. It's true that for gravity, it's this part of the orbit that makes sense, and this part doesn't make sense. This doesn't make any sense, see? But this makes sense. But for the gravity case, it's the one that goes across here. And the same law comes out in the end, because this formula is the same triangle. The same answer in the end, but the different part of the orbit is involved. It's the same for gravity. Yes, exactly. If you knew how the comet is aimed, then the only change made for the thing is this, that the angle of deflection of a comet in coming toward the sun aimed at a distance b from the sun. You understand what I mean? It looks like it's going this way very far out, where this is a distance b that defines the thing. And if you know the speed of the comet, supposing that it has a speed, it was hyperbola, because a lot of comets are not, they're more like parabolas or enormous ellipses. But supposing it were shot from outside, then this is the same, but the z is gm, because it's the force per unit mass times r squared. And they just put gm in. It's the same formula. So you have the relation for the deflection in a hyperbolic orbit. I should have said, I didn't say, that Rutherford was no good at all in mathematics, and he had to go to friends to get this form, and he was very impressed with their ability to calculate that. But I didn't say that. I forgot. Other questions? You want me to show you some blackboard or something? Did I erase? Huh? Yeah. Yeah. Okay. This is a circle. When there's a circle, that's the same circle as that. You okay up to here? This diagram? I erased an important diagram over here, which is the orbit. Can you see it? See it in here, the diagram? There's a diagram here. With the orbit and the velocity Vp. That belongs with this picture. They belong together. Because when this angle is theta, and this point is capital P, then this is the velocity in the orbit. And that's in this direction. So there's a connection between these two pictures. The connection is that when the particle is around the orbit at a certain angle, then the velocity can be calculated by drawing this picture, by taking this standard circle and taking an angle theta here. And this line will always represent the direction and size of the velocity.
This orbit is not the actual orbit.
Yes. No, it's an ellipse. It's this. That's the orbit. And this were just drawn over again smooth, instead of with sharp corners. So this is the orbit, and this is the circle. The polygon becomes very fine and looks like a circle. And this beep, 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 is the orbit. So this was supposed to be that drawn with a fine scale. I mean, you use much smaller intervals of theta and do the thing over again, and then you see this. So that you have that the velocities are on a circle, but the center of the velocity diagram, the origin, is not the center of the circle. And so the theorem, the idea is that in a given moment in the orbit, when you've swept an angle theta, that you go an angle theta inside this circle, and this is the direction of the velocity, that these are parallel. So since we've determined the direction at every angle, we really have a differential equation that determines the orbit. And now I have to solve that. I have to find what curve it is that has the property that the tangent will always be perpendicular to a line drawn here, not parallel to this line. This tangent has to be parallel to this line because it's the velocity vector for the same angle. Just for the same angle. Well, the angle is drawn inconveniently. It's at right angles to the position of the other angle. So in order to superpose them, I turn this diagram 90 degrees so that it's easier to understand. That is, if you draw this line parallel to the radius vector, and then this will be perpendicular to the tangent. Perpendicular because I turned the thing over. So that means that the tangent to this curve, whatever it is always at right angles to a point to a circle from an eccentric point. And then it's finished, because over here we demonstrated that if we draw a point to a circle and then an eccentric point, the perpendicular to this line to the eccentric point is always a tangent. So it's this ellipse which solves that problem. No? Yes, sir. You don't understand that? Well, do you know that? Do you understand that?
No, I don't.
Okay. Very good. You understand that changes in the velocity in equal times are inversely as the square of the distance.
That's what you're saying.
Precisely. Right. Now, just think about it. That means that change in velocities are proportional to the small time interval and inversely proportional to the square of the distance. That means that if the time intervals were proportional to the square of the distances, the change in velocities would be equal. Isn't it? I mean, don't write it, because the whole idea of this, for the fun of it, is to try to think in an old-fashioned way. Because this is the way they used to do all their analysis. They never wrote this stuff. They would argue like this in the air. It's very hard. And so they have equal changes in velocity in times proportional to the square of the distance. Is the same statement as that the change in velocity. They would have said it slightly different. They would have said the change in velocity are proportional to the interval of time and inversely as the square of the distance. And that means that if the time is proportional to the square of the distance, the change in the velocities are equal, which is about the same. And then you'd say, but since for equal areas the times are proportional to the square of the distance, that means that for equal angles the change in velocities are equal. It would be a long little, and it would be very tightly written, in a few lines, that you have to go like this and think, and it comes out. I tried to imitate the style of the old books. To some extent, yes. It's hard if you're not used to it, but it's an interesting style of analysis. Yes, sir. Right. How'd you like that one?
I thought for a moment there
that you understood it.
Go right from there to this.
No. How can I get to there?
Because,
if you can, we're in.
well, I don't know. It's a triangle. This triangle is equal to that triangle.
That's right.
This
You got
triangle
that. You got it.
Is this distance from this base to that point.
That's right.
That height
Yes.
has to be the same as that height. No? No.
No, because this length is not the same any longer as that length. But that's inversely. The velocities are inversely. I'll tell you why you can't get it from that. Because you haven't used the inverse square law yet. To get up to here, all we've used so far is that the force is directed toward the center of the circle. Toward the center of the sun, but it could be any force law whatsoever. So this law of equal areas only proves that the force is in the direction of the center. And therefore, no matter what you do, you'll never get the ellipse out of that, because it could have been a different curve from a different force law. So we must insert the law inverse square somewhere. And the secret idea is that that's very simple to state. It means that equal changes of velocity occur in equal angles. That's the inverse square law.
Did you deduce from the equal changes in velocity in equal time?
No,
That's the equal areas law?
No, the other way around. First, if you remember, I proved that the equal areas held by drawing those pictures. This one, that the areas were equal in equal times. It was the first thing I did, and I had no use whatever of the law of gravity yet, except the force is toward the center.
But you got the equal areas using the equal changes in velocity?
No. Only that this is in the direction of the sun. I don't say how big it is.
Okay.
And I had never had any. I hadn't gotten that far yet. So this is toward the sun. That means this is parallel, and so these triangles fit as indicated, and so on. And therefore, this area equals that area. So it's equal areas in equal time if it's directed toward the center. That's the conservation of angular momentum. It has nothing to do with the force law.
This is what I'd seen. This is
right.
equal to that.
No.
This distance here, AB is equal to BC.
No. It's equal to B little c, but it's not equal to BC.
That's the trouble.
Okay, otherwise you're in trouble, yes. Now, then, of course, after I find equal areas in equal times, then using that law, I deduce. I use that to deduce that there are equal changes of velocity in equal angles. See, I used it here, because from here to here, equal angles means areas proportional to the square of the distance. So equal angles means times proportional to the square of the distance. But in such times, proportional square, this is a change in velocity, are inversely proportional square and proportional square, so they're independent. So that means that equal change of velocity occur in equal angles in the orbit, and then the rest of it makes this diagram into a polygon, and the velocity diagram is a circle, and so on. Huh? Well, not very easily. I forgot to pull down that drawing that I made so carefully so you could see it was the same. It was the same thing. But I suppose you remembered that it was something like that anyway. Actually, I even did construct it again here to show how it worked. To make the perpendicular bisector, that'll certainly be a solution.
That was just for perpendicular bisector.
That's right. Why not? Yes. Just to show that's it. If you happen to do that and construct such a line, it'll satisfy all the conditions, so that's the answer.
Right.
But why a perpendicular bisector? It's like these constructions, geometrical proof.
Yeah,
you never can tell the guy why you drew that line. That line only is the answer. I mean, yeah, you can't... that's the trouble with these. They're not trouble, really. They're very... they're kind of elegant. I took a long time to find that. See, I saw when Mr. Fano had done this business about he was trying to reduce this law here for Rutherford for a book he was writing to make everything simple for so he tried to do it this way, and he got the circle business, and he went through all this to get to the circle. I thought that's very remarkable. It's a circle, and I always wanted to see if I could prove this orbit was an ellipse, because you can explain to people who don't know much of the physics, the early history, how Newton discovered it, of Kepler's laws of the equal areas, and it means it's toward the sun, and all this stuff. And then the key, they always ask then, well, how do you see that it's an ellipse if it's the inverse square? Well, it's goddamn hard. There's no question of that. But I tried to find the simplest one I could. It's still too hard for an ordinary human being. But it's kind of fun. Yeah.
Exactly.
The radius of that circle. I call it a V because it's a velocity. It's a velocity diagram, and the radius is called V sub r. It's not the velocity of anything. It's just a length. I call it whatever I want. It is in this circle here. This is the velocity at the point P, but I call V sub r the velocity, this distance on this diagram.
Well, I mean, when this particle opposes,
V isn't. Yes. No. I should have called it U or script R. It would have been better. It's not a velocity. It's a mistake.